Rational functions are another type of function that we're going to discuss. We've talked about polynomial functions, and polynomial functions have the form ax to some power plus bx to some power. You can call it whatever you want, a1, a2, but they have coefficients and then they have degrees of x, and they have up to, we've looked at up to the fifth power. So we looked at quadratics, then we looked at cubics, then we looked at quartics, and then we looked at a couple that had a fifth degree. But now we're going to look at rational functions, and there's two forms of rational functions that we have to know. One is going to relate back to some of the stuff we did with trig functions in Pre-Calc 12a. So if you know about a, b, h, and k, then we're going to use that, but in the form of taking 1 over x. So you'll notice here in this form you have a, b, h, and k, but the general form of a is 1, b is 1, h is 0, and k is 0, which we're used to from different things. It's a basic rearrangement of this y equals 1 over x. So that's sort of the basic rational function. It's the smallest version of a rational function, and then we move that around using vertical and horizontal translations and vertical and horizontal shifts. The other form is a form where you have actually a polynomial function over a polynomial function. So you might have, just as an example, y is equal to x squared minus 5 over 3x minus 2. That's a rational function. So we're going to look at both forms. We're going to start looking at just the a, b, h, and k vertical horizontal transformations of 1 over x. So we're going to look at that. And then once we've sort of done a few practice questions with that and understand that concept, then we're going to look at the second form. All right, so the first form looks at transformations of y equals 1 over x. We just said that, and this is what y equals 1 over x looks like. Okay, and it's important to know the basic shape, because all transformations of 1 over x are going to share that basic shape. It might flip on the x-axis, it might flip on the y-axis, and it's going to move around, but the basic shape is going to stay the same. And so there are some basic properties that we are going to try to assess what happens when we move this around. And those basic properties are, you will notice a horizontal asymptote. And what that means is you have a line that, if I sort of draw a line here, that the function is approaching when x is either getting really big, so going to positive infinity, or x is getting really small, negative infinity. And that is called the horizontal asymptote. And in this function, the function that we're looking at, 1 over x, that horizontal asymptote has an equation y equals 0. It's the x-axis. We also have a vertical asymptote. You'll notice if I take this line again and just draw it this way, you'll notice that there is also a line that these are approaching in the y. So this one is going down, the function's kind of going down towards negative infinity, and then it's starting up at positive infinity and coming back down. So this is called a vertical asymptote, and you would have seen those when you're doing tangent graphs in Pre-Calc 12a, if you remember that. And otherwise, you might not have seen examples of functions that have those vertical asymptotes, but that's what it is. And that equation is just x equals 0. It's the y-axis. And what's going to happen is those asymptotes are going to shift. They're going to move, and they're going to move based on our parameters, a, b, h, and k. All right? And then we have a domain and range. And the domain and range, we've talked about that with any function we look at. The domain is the values of x that you're allowed to have. And really, the domain here is all values of real numbers. So x belongs to real numbers, except that x can't be 0. And the reason x can't be 0 is you'll notice that this is not ever touching 0. The function's going up here towards 0, and it's going down here towards 0, as x approaches 0. But at x equals 0, there is no value for y. All right, we're saying it doesn't exist there. And that is because if you plug x equals 0 into this, you get 1 over 0. Okay, and division by 0 does not produce a real number. So that's why we have that vertical asymptote, and that's the domain. The range, you'll notice, is a similar thing. There's no time where it actually touches the x-axis. It comes close to it here, and it's getting closer here, but there's no time where it actually touches the x-axis. So our range is y can be any real number, all of these, all the positive y values and all the negative y values, but it isn't 0. Okay? So those are the 4 things that we look at. You'll notice, you might be saying, well, we always looked at x and y intercepts. Well, we do sometimes, but here there actually aren't any. There's no y intercept because y can't be 0. Sorry, x can't be 0, y-intercept. And then there's no y-intercept because x can't be 0. So you have both y can't be 0 and x can't be 0. So if x can't be 0, you can't have x-intercepts. And if y can't be 0, then you can't have intercepts there on that axis either. And so you end up with no x or y intercept. Now you will, if you move this around, get an x and y intercept. So if you can find the x and y intercept, and the question asks you to, then you can do that. But there are none in this particular case for this particular graph. So the basic graph has a horizontal asymptote, a vertical asymptote, and a domain and range, and they're all centered at this point around 0. Okay, so then the question is, well, what happens when I do change a, b, h, and k? All right, so what happens when I add in numbers either to a, meaning you would get something like 2 over x, or 3 over x, or even minus 3 over x? What happens when I add a number here? And what happens is you get a vertical stretch. So that means that the graph is going to get skinnier, or it's going to drop more quickly. And I'll just show you an example. If I was to graph, let's say 3 over x, it looks like this in comparison to just 1 over x. And we'll make that a different color so you can see the difference. So it gets wider here, or it drops a little less steeply, I guess, for lack of a better term. So you can see the difference there and the distinction between 3 over x. And then if you have a negative, what happens? If I change it to a negative, is it's going to flip over the x-axis. So that's what we call a reflection in the x-axis. And what it looks like is that instead of going down and then coming down again, it's going up and then coming up again. So it just flips over the axes. All right. So if you want to compare it exactly, if you look at minus 3 over x to 3 over x, the only difference is it's a reflection in the x-axis. In other words, you take this and flip it over the x-axis, it looks like this. And the same thing there. Okay? So that's what A does. If you look at B, B is a horizontal stretch. And a negative means that the reflection happens in the y-axis. So again, if we just change this, instead of it being, we'll put the 1 back on the x, but b is down here multiplied by x. So let's say I put a minus 3 there, and then I just show you what, in comparison to 1 over x, what happens. Okay, so this is 1 over x, and then this is 1 over minus 3x. So you can kind of see that it's flipped, but it's flipped vertically. So it's gone from here, it flips that way. All right, and the other one is bent this way, so now it's flipping around. Okay, so that's what it means by a reflection of the y-axis. You're flipping it over the y-axis as opposed to the x-axis, and then the minus 3 is just making it steeper or less steep. If you put in a 2, right, you can see that it looks like that. If you put in something that's smaller, so let's say 0.5, then you'll notice it sort of reaches out again. So it's called the vertical and horizontal, sorry, it's called the horizontal stretch, but the A and B are the vertical and horizontal stretches. So they just make the graph either wider or skinnier, for lack of a better term. They make it steeper or less steep, and they stretch it in either the horizontal direction or the vertical direction. And then the horizontal shift and the vertical shift come from H and K, and all they do is just move the graph left to right. That's what the horizontal shift does, and the vertical shift moves it up and down. So what does this all mean in terms of what is this effect on the horizontal asymptote, the vertical asymptote, the domain, and the range? How does that change those things? And what it does is it changes the vertical asymptote from x equals 0 to x equals h, and the horizontal asymptote to y equals k. And then the domain and range is just x belongs to real numbers, but x can't be h, and y belongs to real numbers, but y can't be k. So all it does is change the zeros to h's for x and k's for y. The a and b do not affect the domain and range, and they don't affect the vertical and horizontal asymptote. And the reason they don't is because they're multiplied, whereas h and k are added. All right. So how do I actually draw this and state everything? So let's just go through an example of this. So the question is this. It wants you to draw this and state all of the information from it. So the first thing you need to do when you look at a function like this is recognize what is the value of a, what is the value of b, what is the value of h, and what's the value of k. So a comes from here. This is our a value. It's whatever is in the denominator. B is out in front of the x, and since there's nothing there, generally this would be in brackets, right? And there would be a number out front, but since there's nothing there, B is 1. This is h, but you switch the sign, and then this value is k. That's where we're getting those from. So the number that's added or subtracted to the end is the k value. That tells you then what the transformations are. So there's a vertical stretch of 6. There's a horizontal shift of 2 to the right. You'll sometimes hear this called a horizontal translation. And if you want to do that, you can call it a T, and same thing with vertical translation. And then it's shifting 3 down. So it's moving 2 to the right, 3 down, and then it's stretching by a factor of 6. So what does that actually look like in terms of the horizontal, vertical asymptotes and domain and range? Well, the domain becomes x belongs to real numbers, but x can't be h. So h is 2. And the vertical asymptote is x equals 2. And remember, on your graph, what that looks like is actually a vertical line that we draw in there with a dashed line. So it's not actually on the graph, technically, but it's just to emphasize where it is. And then the same thing with the horizontal asymptote and the range. They become k. So y can't be minus 3, but y equals minus 3 is my horizontal asymptote. So I've stated the things that it wants me to state, and then if you want to find the x-intercept, you would let y equal 0 and solve for x. So there is an x-intercept here, and there is a y-intercept because you let x be 0, and you'll get a y-intercept. So you can find those in this particular instance. You can't always find them, so we don't generally ask you for them. But if you were to find them or wanted to find them, you would just let x be 0. So that would give you 6 divided by minus 2, which is minus 3. Minus another 3, so your y-intercept would be minus 6. And if you let y equal 0, you get 3 divided by 6, and then multiply, then flipped and solve that way. In other words, you would go like this. If you wanted to find it, you go 0 equals 6 over x minus 2, and then minus 3. So you get 3 is equal to 6 over x minus 2. That means that 3 times x minus 2 is 6. Which means that x minus 2 is 2 if you divide by 3, and so x is 4. All right. So your y-intercept is and your x-intercept are from those points. All right. But you don't always have them, and because you don't always have them, you don't always get asked for them, if that makes sense. So that would be your x-intercept, right, when y is 0, and then your y-intercept was when x is 0. So your y-intercept, if I just erase this and kind of show you, you would let x be 0. So you get y equals 6 divided by minus 2 minus 3. And I know I just said this, but just so you can see what I was talking about, you get minus 3 minus 2, which is minus 6. So you can find an x and y-intercept. The x-intercept is 4 and 0, and the y-intercept is 0 and minus 6. But you're not necessarily asked for them. So then the question is, how do I move this around? And the way that I do this is only one method. You can use other methods, but the way I do it is I start with small values. So 1 over x, I pick these x values, but you can use all of them every time. In other words, you can use these 5 points each time you do it. So I go -2, and then if I flip that over, I get -1/2, -1 and -1, 0, and does not exist. 1 and 1, because 1 over 1 is 1, and then 2 and 1 over 2. And then what I do is I multiply y by a, and I divide x by b. So the x values, because they're getting divided by 1, they're going to stay the same. And the y values are getting multiplied by 6. So we just multiply them by 6. So -1/2 times 6 is -3. -1 times 6 is -6. This stands for does not exist. That's my vertical asymptote, right? It's at x equals 0. So you can't multiply something that doesn't exist, so we just leave it as does not exist. And then we multiply 1 by 6, and 3 comes from 6 times 1/2. So we multiply by a, and we divide by b. So the x values are all divided by 1, which is why they're staying the same. If b was 5, they would all be divided by 5. Okay? And then we add h to x, and we add k to y. So h was 2, so we're going to add 2 to all of these numbers. And y is going to get -3 added to it. So we're going to subtract 3 basically from all of these. And when we do that, we get a series of points. Okay, so we add 2 each time, so we get 0, 1, 2, 3, 4. And then we subtract 3, so we get -6, -9, doesn't exist, 3, and 0. And then all you do is plot these points, okay, along with these two values. So we plot x equals 2 first, that's our vertical asymptote, and y equals -3, that's my horizontal asymptote. So we graph those two first. Then we plot the points that I just found. So the points are 0 and -6. There's that one. Then 1 and -9. So 1 is here and -9. And then I have 2 and does not exist. So I've plotted that already. Then 3 and 3 is right here. And then 4 and 0. And you'll notice actually this, we actually had in our table. And that's the x-intercept, which also showed up in our table. That doesn't always happen, but it's nice when it does. So then we just connect the dots. So we know that this it can't cross this, so it's got to come down here. And then this is our vertical asymptote, so it's got to start up here and go down. And that's how you draw a rational function using transformations. Okay? You're going to be asked to state the vertical and horizontal asymptotes in the domain and range. You're going to be asked to describe the transformation. So you're going to do a vertical shift and vertical stretch, or vertical translation and vertical stretch, and then horizontal shift and stretch, or translation and stretch. And then you're going to be asked to draw the graph. And to draw the graph, I'm saying use these points every time and just multiply y by a and divide x by b, and then add h afterwards. So you're adding h here and you're subtracting k to these points to get those. So we'll go through one more example and then we'll call it a video, and you can go and look at your own textbooks and work on some questions from there to get the hang of this. But there's another question. So the first thing I like to do is I like to state a, b, h, and k. A comes from here, so a is going to be 4. B comes from out here. There's nothing out here, so b is going to be 1. H comes from here, but opposite sign, so h is going to be -1. And then k comes from here, so k is going to be 5. Then I like to describe the transformation. So what does that mean? It means that there's a vertical stretch of 4. There's a horizontal stretch of 1, if you want to say that, but it's easier just to leave it because it's not actually doing anything. And then there's a horizontal shift of 1 to the left because it's negative. So it's going left as opposed to right. And then it's going up. So there's a vertical shift of 5 up. And again, you can call these translations if you want to. And then I look at my parameters, my sort of descriptors of the graph. The vertical asymptote we said was x is equal to h. So h is -1. And the horizontal asymptote is y equals k. So it's going to be y equals 5. And then the domain is x just can't be -1, but it can be everything else. And the range is y can be everything else, but it can't be 5. And then I go to draw the graph. Okay, so that's all the information. And generally, that's all you're going to be asked for. You might be asked to find the x and y intercepts, but you're not in this question. But then I want to graph it. So I start my table by just listing these points. These are arbitrary in the sense that you can use other points. You pick the x values. The y values are determined by this 1 over that value. But I think it's easier to use smaller numbers, and it's also easier just to remember those if you're consistent. So I use -2, -1, 0, 1, and 2. And really, excuse me, it doesn't matter what numbers you use, but you're going to multiply the y values by a. And if we go back up here for a second, a is 4. And we're going to divide by b, but b is 1. So the x values are going to stay the same, and we're going to multiply all the y values by 4. So -1/2 times 4 is -2, -1 times 4 is -4, 1 times 4 is 4, and 1/2 times 4 is 2. And then we're going to add h, and we're going to add k. So we're going to add 5 to y, because y gets k added to it. And then we're going to add -1 to x, because x gets h added to it. So -2 minus 1 is -3, and -2 plus 5 is 3. And then we just go all the way down. We get -2 and 1 when we add -1 and add 5. And then again, that does not exist. That's just our asymptote. It's following through. So all we're changing is the x value. And then we get 0 and 9 and 1 and 7. And then all you do, again, is graph this. So you graph these two values, x equals -1 and y equals 5. Okay, so there's my y equals 5 right there. And there's my x equals -1. And then I plot these points. So -3 and 3, -2 and 1 is right here. And then this is my does not exist. So I've already drawn that. Then I have 0 and 9. And then I have 1 and 7. Okay, and I just then connect the dots. So that's where this is coming from. It's just going down through those numbers and coming down through those numbers. And that gives me my graph. There's my graph of that function. So that's how you draw rational functions that are in this form. They're transformations of 1 over x. So they're all going to look like this to some extent. They're only going to have 1x, and it's going to be in the denominator. All right? So we're going to take some time to try some questions from your textbook. So I'll let you try those, and then we'll look at what happens when it's the other form.